Yep. All right. Now that you've been motivated to want to learn about limits, let's look at an informal view of the limit. So we're going to get to the nitty gritty here. So I'm just going to read this first paragraph here. It says, if the output values of the function f of x can be made as close as we like to some number L by making the input values x as sufficiently close to some number a, but not necessarily equal to a, then we write the limit and we write this. All right. Now, just reading that seems very convoluted. Believe it or not, this is the informal view of the limit. The formal view of the limit, you can Google search it if you want, has to do with epsilons and deltas. And if you want to just get your doors blown off a little bit, Google search it, all right? But we don't need to make it that complicated. So let's just take a look at this. We'll start with this. This is read the limit of f of x as x goes to a from both the left and the right is equal to some unique number L. That's how we read this. Now, what actually is going on? Well, that's the purpose of this picture, and hopefully it makes sense to you. So we're basically saying as we drive our input values of the function close to A, and it's a two-pronged effect here. So first, as our x values get close to A from the right side, what are our corresponding functional values doing? That's what the purpose of these dots is. So like here's an x value. There's the corresponding functional value for that x value. Well, now let me pick an x value closer to A. Okay, I'll pick that one. There's the corresponding functional value. Let me pick another one closer to A. All right, well, there's the corresponding functional value. Let me pick another one even closer to A. There's the corresponding functional value. So now I only happen to put 4 dots here, but the idea is as your x values get closer and closer to A from the right side, what are your functional values getting closer and closer and closer to? So in other words, what y value are they getting closer and closer and closer to? Think about like a little limit buggy up here. That's my limit buggy, right? As x is driven to A from the right side, this little limit buggy, this corresponding functional value buggy, is going to track along the curve what y value is he getting close to. And hopefully you're going to say, in this case, looks like he's getting close to L. So that's what we call the right-hand limit. Well, now this is a two-sided idea limit, right? It's not only as x gets close to A from the right side, but it's as x gets close to A from the left. So you got to take a look at that. So as our x values get close to A from the left side, again, here the demonstration with these dots is here's an x value, there's a corresponding functional value. Here's an x value, corresponding functional value. Input, corresponding output, right? So as your inputs get closer and closer to A from the left side, what are your corresponding functional values getting close to? So there's a little limit buggy over here, right? And he's going to track along the curve. What is he tracking to? Well, hopefully you're saying as x gets close to A from the left, he's going to track, again, to this y value, which is L. Okay? So since the limit from the right and the limit from the left is L, we say that the limit is going to be L. Right? So L is just a unique y value, a unique functional value, all right, that we're approaching as our inputs get to close to a certain value A. All right. Now, there's a couple things in here that we don't want to get too much into, but if you reread this, it says, but not necessarily equal to A. And the idea of that is you don't necessarily ever have to get to this black dot. Okay, or the black dot might not even be there in certain functions. You don't have to get to it for there to be a limit or for the limit to be L. You might be saying, what the heck are you talking about? Well, if I was in class, I would do this little demonstration where I'd say, hey, here I am, and here's the wall. And I'd say, all right, you know what? I'm 12 feet away from the wall right now, and I'm going to do the following. I'm going to move to the wall, and every time I move to the wall, a move requires me to just take half the distance. So if I'm 12 feet away, I'm going to make one move. How far away am I now? 6 feet, right? And now I'm going to keep doing that. So then I'm going to make another move, and I'm going to be 3 feet. Then I'm going to make another move, and I'm going to be 1.5 feet. And I would ask the question, do I ever get to the wall if I walk in this manner, if I continually have the distance between me and the wall? And hopefully you would say no, right? Because as soon as I'm about to get to the wall, my next move is to have the distance between me and the wall. So as long as I'm able to step small enough, and that's debatable that I would be able to, but as long as I'm able to step small enough, in theory, I never actually get to the wall. So what I say is I approach the wall. The wall is my limit, right? And so that's the idea that I want to drive home to, that a limit is something that you approach and you don't necessarily have to get to. And what that translates into functions is a limit is a y value that you get close to, even though the y value might not potentially exist, although that's hard to see in this picture right here. But we will get to it. As long as you get the idea that a limit is something we approach, then you're going to be good. Okay? All right, so the next thing I want to look at is more notational. All right, this is kind of like, hey, this is what it is. So if you think about what we did here, when I explained this limit, I explained it in a two-pronged approach, so to speak, right? There was a limit from the right and a limit from the left. So what if we just want to talk about the limit from the right, right? Because when you write it this way, this is the limit as x goes to a from both sides. So if there was a need, or if I just wanted to talk about the limit from the right, we can kind of not look at that just yet, I can do it notationally, all right? And we call these one-sided limits. So one-sided limits. And really all I'm giving you right here is just notation. So watch what it is. You'd write the limit of f of x of some function as x goes to a. And if you want to go just from the right side, you do a little superscript plus like that. So this is read, the limit of f of x as x goes to a, strictly from the right. We can say it equals some number. Maybe I'll call it L1. All right, so this is the limit from the right. If I want to do the limit of f of x as x goes to a strictly from the left, then I would do a superscript minus sign right there. We could say that equals some other value, L2. All right, so this is a right-hand limit. This is a left-hand limit. In your notes, it has it all written out for you, so I'm not going to rewrite any of that. All right, so now it should be real important to realize and understand kind of inherently from what the definition before was, is these guys have to be the same in order for the two-sided limit to exist. All right, so that's really important. So the limit from the right must equal the limit from the left, all right, in order for the two-sided limit to exist. All right, now if that's not the case, so in other words, maybe we'll write note or key here. All right, if the limit of f of x as x goes to a strictly from the right does not equal the limit of f of x as x goes to a strictly from the left. So in other words, limit from the right doesn't equal the limit from the left. If that happens, then we say the limit of f of x as x goes to a does not exist. So the moral of the story is whatever you're approaching from the right, you have to also be approaching that same value from the left. Otherwise, we can't talk about this two-sided limit. All right, so that's one of the ways in which a limit wouldn't exist. And there's going to be other ways, but for now, that's that. So just to stick along with this theme of one-sided limit notation and also to revisit absolute value of x, let's do a quick little problem. All right, so I always like to start off in calc class asking everyone, what is absolute value of x equal to? Right? Everyone will say x because x is positive, all right, and they're in calculus. And that always blows my mind because then I'll say, all right, well, so it's just always equal to x, and they'll say, yeah. And say, all right, well, what does the graph look like? And the whole world knows what the graph of absolute value of x looks like, right? It's the v, right? So if I was to graph absolute value of x, it would look like that. Now, that's not the graph of x. If I was to graph x, it would just be this line right here and continue down here, not this red part, okay? So you're like, well, what is this really the graph of? Well, think about this. This blue portion, that's the graph of x. That's going to be, y equals x, but only when x, right, or for x values that are greater than 0. But if I look at this isn't the graph of x. This is y equals negative x, but it's only turned on for x values that are less than 0. So for x values that are less than 0, we have this y equals negative x graph, right? And for x values that are greater than 0, we have this y equals x graph. And now you're like, well, what about when x is 0? You can actually just say that it's 0 when x is 0, or you can just do that, right? Because that would work, or you can put the or equal to there, right? But the moral of the story here is that the graph looks like this, and this says right here that absolute value of x doesn't always equal x. In fact, it equals x when x is positive, and it equals negative x when x is negative. And I could write 0 when x equals 0 here, do a third piece, but a lot of times we just get lazy and say, hey, put an or equal to here, right? Because 0, or here, and negative 0, they're both 0, all right? So that's what absolute value of x is equal to. And hopefully when you go back to the graph concept, that'll ring home. Now, you might have this little conundrum in your brain that says, I thought absolute value of x was always positive, right? And yeah, it is, and that's what this says. Think about it, right? If you were to do the absolute value of negative 2, right, what is that? Everyone knows it's 2, but how do you get it? When the input is negative, like here, it's negative 2, you have to negate the input, right? You have to negate the input in order to get that positive. So that's actually what this is saying. All right, so that's your little refresher on absolute value of x because it pops up a lot. All right, so now what if I wanted you to do the limit of absolute value of x over x as x goes to 0 from the right, and then I'm going to want you to do the limit of absolute value of x over x as x goes to 0 from the left. I want you to do that. And then finally, I want you to do, if possible, the limit of absolute value of x over x as x goes to 0 from both sides, right? So we're just kind of getting a little review of our notation here. Well, I really only kind of explained the limits to you from a graphical standpoint, so it would make sense that you'd have to graph this. You'd have to graph the absolute value of x over x graph. So how the heck would you do that? Well, again, let's rock and roll here. Let's see a little real estate over here, right? Whenever you're going to do any sort of analysis on an absolute value graph, let me just erase this since I don't want it to confuse us anymore, all right? Whenever you're going to do any sort of analysis on an absolute value graph, it usually behooves you to rewrite it as a piecewise function. So now we just went over that absolute value of x is sometimes equal to x. So I can rewrite this as one piece would be x over x, right? Which, by the way, x divided by x is 1. But remember, this is only equal to x when x is greater than 0, okay? Now, sometimes absolute value of x, as we just saw, is equal to negative x, right? So this is equal to negative x sometimes, and then the bottom is x. So negative x over x, that reduces to negative 1. Now, that's only when x is less than 0. So now in the previous problem, I said you could put the or equal to on either one. Well, that's because it was just absolute value of x, but our function now is absolute value of x over x, right? So if x was to equal 0, you'd have 0 divided by 0, so that's not defined. So 0 is not in the domain of this function. So basically what I just did here is I just rewrote this as a piecewise function and got two pieces, 1 and negative 1. So that's actually, if you think about it, going to be fairly easy to graph, right? So if I make a little happy y-axis here and a happy x-axis, basically what we're saying is, all right, for x values that are greater than 0, just sketch the graph of 1. Well, a constant is going to be a horizontal line, all right? So that's going to be just that. Notice I put an open circle here because we're not defined at 0. For x values that are less than 0, you're going to sketch the graph of negative 1, which is going to be that constant right there. So I'll put a little negative 1 there. All right. So this is what the graph of absolute value of x over x would look like. So now you can see why it's kind of an interesting limit problem. So now let's go about doing limits like I did before. Let's start with the right-hand limit. The limit of this function as x goes to 0 from the right. So think about it now. As x goes to 0 from the right, as my inputs go to 0 from the right, what are my corresponding functional values getting close to? What y value are they getting close to? This little limit buggy, as he tracks, what is he getting close to? Well, he's getting close to the y value of 1. In fact, he's just staying at 1. No matter what x value I pick, the closer and closer and closer I get to 0, these y values are always basically 1. Okay, it has nothing to do with what's going on here. Remember, a limit is something that the limit is a y value that the limit buggy gets close to, approaches, has nothing to do with the functional value there. All right, so this limit would be 1. Now, what about the other side? As my x values get closer and closer to 0 from the left side, right, x value corresponding y value, x value corresponding y value, what are my corresponding y values? Are my limit buggy on this side, what is he approaching? In fact, not only is he approaching, he's basically remaining steady at negative 1. He's getting closer and closer and closer, or remaining steady to the y value of negative 1. All right, so this limit would be negative 1. And so now maybe the better question for me would have been for you to ask you this from the get-go. What's the limit of absolute value of x over x as x goes to 0 from both sides? Now, you might say, oh, it's 1 and -1, but you can't say that. Remember, a limit is a unique value. It's one answer. It's what are you approaching from both sides? It's got to be the same thing. And if it's not the same thing, then we say what? Hopefully you said does not exist. So since the limit from the right does not equal the limit from the left, we'd say the limit does not exist. All right, so that's a quick little intro on limits from a graphical perspective with a little splash of absolute value in there. All right, talk soon.